Hello everyone, I am Gabriela Merino from Argentina and I will present you our work integrating multiple information sources for protein function prediction with end-to-end deep learning. The automatic function prediction consists in to use and process protein data from multiple sources in order to feed a computational model able to predict, for instance, which labels or gene ontology terms should be used to describe protein functions. These models are commonly assessed by the community by evaluating their performance when predicting new annotations that the proteins gained during a growth period. Among the set of proteins whose functions want to be predicted, we focus our work on the most challenges that are those referred as no knowledge or NK proteins. Those proteins do not have any functional annotation at the reference time, but they have gained annotations during the growth period. Predicting Go terms for NK proteins from any organism is also a challenging task because when we are trying to do this, the unique information that we will have for most of them and that can be used for our model is their sequences and the organisms from which they belong. To solve this hard task, we propose here DeepGo, a deep learning model for the automatic function prediction of Go terms by integrating protein knowledge. DeepGo consists of two blocks involving several input encoding subnetworks and a classification subnetwork. The input subnetworks are aimed to process each input data in a separate way and encode it into a learned feature space. The set of learned features is then integrated into a single vector that is used as input of the classification subnetwork. This subnetwork has 6 fully connected layers aimed to predict the set of Go terms for each protein. The last 4 layers model the output, taking into account the hierarchy of gene ontology from the most general terms to the most specific ones. The model is trained in an end-to-end fashion using the sum of the binary cross-entropy loss of these output layers as a cost function and the Adam optimizer. DeepGo was trained and tested considering the 3 time points of kappa3. T-1 when training and target protein sets were released, T0 the deadline for submitting target predictions, and T1 when benchmark proteins were collected. Among the set of kappa3 benchmark proteins, we can distinguish those having annotations at T0 referred to as low knowledge or LK proteins and the NK proteins that we presented before. Thus, the datasets for evaluating and assessing DeepGo was obtained by selecting those NK proteins in the kappa3 benchmark dataset. For building a training dataset that allows DeepGo to learn annotations gained during a growth period, we defined the lapse time between the kappa3 release T-1 and the deadline for submissions T0 as the annotation growth period for training proteins. One difficulty that we should overcome when working with NK proteins is that all the proteins that are provided as the training set by kappa3 have annotations at the reference time T-1. Thus, at the end of the annotation period that we defined for training, we can split this training set into 2 subsets depending on if they have accumulated new annotations, the low knowledge or LK proteins, or if their annotations remains unchanged. Those proteins were defined here as no change or NC proteins. As a consequence, we do not have any example of no knowledge proteins for training our model if we only take into account this kappa3 training set. To solve this problem, we analyzed all the UniProt SwissProt proteins that were not in the kappa3 training set in order to identify NK proteins for this annotation period and use them to train our model. Since these proteins were very few for training precise models, we also designed a data augmentation strategy. Thus, for each sub-ontology of gene ontology, we analyzed the set of low-knowledge proteins, LK proteins from the kappa3 training set, and selected those that, for this particular sub-ontology, are no knowledge. It means these proteins did not have annotations at the reference time, t-1, but have gained at least one annotation during the growth period defined for training data. Thus, taking into account the three different sub-ontologies of Go, biological process, cellular components, and molecular functions, and considering two different groups of proteins based on the taxonomic kingdoms, Prokarya and Eukarya, we defined here 6 different prediction tasks that were modeled in a separate way. For each of them, the number of proteins that were available in the training and benchmark datasets are summarized in this table. Notice here that in the 6 cases, the number of true no-knowledge proteins available for training DeepGo is really low. Even more in the case of the prediction of cellular component Go terms for prokaryotic proteins, there are no examples of true no-knowledge proteins in the training dataset. For this reason, using a data augmentation strategy is a must in order to allow us to train models able to predict annotations for this kind of proteins. As we mentioned before, when we are trying to predict the functions of no-knowledge proteins from any organism, the unique information that we have for most of them is their sequence and the organism from which they belong. Thus, the input data that we can use for DeepGo must be based on this information. Here, we defined 3 different types of input data for DeepGo. Input features from sequences were obtained by embeddings of length 1024 generated with ZBEC, and by defining a protein similarity measure based on the pairwise sequence edit distance. The organism taxons were also used as input by representing them with a one-hot encoding vector. The model output of DeepGo, it means the gene ontology annotations gained during a growth period, were also represented here by one-hot encoding vectors. So, in summary, we trained 6 different DeepGo models, each of them involving, at the most, 3 input encoding subnetworks for learning the protein features useful for predicting their functional annotations. All these models were trained under a cross-validation scheme involving 3 folds. The training set was split into 70, 10, and 20% for training, validation, and testing, respectively. Hyperparameters of the networks were fine-tuned by grid search. We focused the optimization process to obtain optimal values for the dropout probability, the batch size, the number of neurons in the hidden layer of all the subnetworks involved in DeepGo, and in the learning rate. The number of epochs was optimized using an early stopping strategy with patience of 10. All model performances were compared and assessed using the Fmax, recall, and precision performance measure defined and used for the CAFA challenges. The performance of DeepGo in training data was assessed analyzing the achieved average scores on the corresponding test partitions. The results obtained for the best configuration of each model are presented here using bar plots. In this case, this graph indicates the results obtained for the 2 models predicting biological process annotations. Each field bar represents the Fmax score achieved by each model, where the color of those bars indicates the different inputs that DeepGo received for doing these predictions. In addition, those unfilled bars indicate the recall and the precision that were achieved when this Fmax scores were reached. As you can appreciate here, the Fmax scores achieved for biological processes predictions were 0.49 and 0.39 for prokarya and eukarya respectively, and at least embedding and taxon information were used by DeepGo for doing the prediction, even more being also necessary to use the protein similarity measure for doing the predictions of prokaryotic proteins. When predicting cellular component annotations, the Fmax scores reached by DeepGo were higher than 0.70 for eukarya and prokarya models. Even more, as is indicated by the dark pink color of these bars, integrating all input data led to achieve the best performance in both models defined by the taxonomic kingdoms. Analyzing the results DeepGo achieved when predicting molecular functions Go terms, we found that for prokaryotic proteins, the Fmax reached was 0.64 and that the best performance of our model was 0.82 and it was achieved when predicting molecular functions Go terms from eukaryotic proteins. Interestingly, the best performance of our tool and the best result that DeepGo achieved when predicting molecular functions Go terms was achieved when the model used only the information that is contained in the sequence embeddings as input. Our results also revealed that DeepGo always exhibited a precision higher than the recall, thus indicating that our tool is able to assign true gene ontology terms to the proteins with fewer false positives. The results of the evaluation of the DeepGo performance when predicting Go terms of no-knowledge kappa-3 benchmark proteins are summarized in this table. As you can see here, we have the 6 different tasks that we defined before, the performance measures achieved for each of them, and we also have the overall Fmax that indicates the weighted average of prokaryotic and eukaryotic Fmax scores. As it can be seen here, the Fmax scores reached for predicting biological process terms were 0.32 and 0.35 for prokarya and eukarya, being 0.34 the overall Fmax reached by DeepGo. A similar value was observed for predicting cellular component terms in the case of prokaryotic proteins. Remember, a special case, because for this prediction task, no true no-knowledge examples were presented in the training set. The best performance of DeepGo was for predicting cellular component terms of eukaryotic proteins, 0.58, and molecular function terms of both prokaryotic and eukaryotic organisms. In particular, for both cellular component and molecular functions, the overall Fmax that DeepGo reached was 0.55. In addition, and same as during model training, the precision of our model was mostly higher than the achieved recall. Finally, we compare the overall Fmax scores reached by DeepGo for each ontology against those reported for both the top-performing methods and the baseline methods of kappa-3. As it can be observed here in this bar plot, DeepGo performed in the top 5 kappa-3 methods for biological process and for cellular components. Moreover, DeepGo is the second best method when predicting molecular function terms of known-knowledge proteins in kappa-3 benchmark dataset. All our results indicated that our method has a performance that is competitive to the top 5 performance methods on kappa-3. We also identified that DeepGo is the second best method when predicting molecular function annotations, And we also found that the data augmentation strategy that we designed allow us to train precise models. As future works, we propose to train DeepGo for predicting gene ontology terms of low-knowledge proteins and to assess different alternatives of data augmentations. Thank you for your attention, and thank you to all the team that have participated in this work.